Hello everybody. In this video we're going to talk about how to draw Lewis structures of atoms. And this is a type of nomenclature that is kind of the linking thing between the chemical symbols we've already been familiar with and the type of condensed nomenclature that we saw last week when we're doing organic chemistry. So Lewis structures of atoms are essentially the same as the atomic symbols, but with explicitly drawn out valence electrons. So here are some examples. If we have sodium, it has one valence electron. I'm going to draw just one little dot right there. And that dot could be anywhere. It could be any one of those positions, top or bottom. You can see that if I draw out carbon, I'm going to have 4 of them, and I'm going to put one dot in each one of these positions, either to the left or right, or top or bottom of the carbon. Once I go past 4 electrons, like in the case of nitrogen, I'm going to start to double them up. And this is consistent with what we saw for orbitals, where we first fill 1 electron into each orbital and then we start to double them up. So here in the case of nitrogen, we're going to have one doubled up, what we call a lone pair up here. And then in the case of bromine, you can see we're going to wind up with 3 lone pairs and then 1 lone electron here. And that lone electron again could have been in any one of these other positions, so long as we had the doubled up ones in the other positions. So when we're drawing Lewis structures of ions, we're going to remember to add or remove the electrons and add charges when drawing electrons. So in the case of sodium, we're going to remove that 1 electron because we know that sodium has a +1 charge. You can see it now has no valence electrons, and we're going to write up here that 1 plus to indicate that it is an ion. For nitrogen 3 minus, we're going to double up the remaining positions around nitrogen, and we'll write 3 minus up here. We can see it now has 8 valence electrons. And the same with bromine. We're going to fill out that last electron and then put the 1 negative there. And you'll note that because these atoms are trying to either fill or empty their outer valence electrons to get their octet, you're typically either going to wind up with a species that has no dots around it or one that has 8 dots around it, depending on whether or not it took electrons or removed electrons to form that ion. So let's talk about what not to do. What we're not going to do is we're not going to forget to remove the dot that indicates that electron when we're drawing sodium 1 plus. So always remember that you're going to have a different number of dots when you have an ion as compared to a neutral element. We're not going to double them up before we put 1 dot in each of the positions. And we're not going to ever draw more than 2 dots in any one of the positions because our orbitals are only able to hold 2 electrons. What we can do is we can place the dots in any one of the positions that we want, whatever is convenient for what we're trying to convey. And again, it doesn't matter which dots we pair off. Again, you can pick whatever ones are convenient for what you're trying to draw out at the moment. So let's take a look now at how to draw Lewis structures of molecules. I'm going to remind you guys once more that covalent bonds are formed when a set of electrons are shared by 2 atoms. and I'm going to tell you that when drawing Lewis structures, simple covalent molecules are drawn by pairing off electrons. So let's look at some of our simplest cases here. If I have a lone hydrogen, it has 1 valence electron. I have a lone chlorine molecule. It has 7 valence electrons. You can see that I chose to write the single dots next to each other. And so if we smush these two together, we would get something that looks like this, where now these 2 electrons are being shared by both the hydrogen and the chlorine. These are now our bonding electrons. And we can write that out explicitly by using a line that indicates a bond. The remaining electrons on chlorine we call our lone pair electrons. If we look at the case of water, we could start off with 2 lone hydrogen atoms and 1 oxygen atom, and we could pair them off, where one of them pairs off with this guy and one of them pairs off with this guy. We wind up with a structure that looks like this. And again, we can be more explicit by drawing out those bonding lines here. And we see that oxygen has 2 lone pairs left on it. Sometimes it is possible to pair off more than just one set of electrons, and that leads to what is known as multiple bonds. So if we look at the case of oxygen here, if I have 1 lone oxygen, another lone oxygen, each one has 2 non-paired up electrons. I'll pair off the first ones and I'll get something that looks like this. I still have 1 and here and 1 here. I can pair those off and I wind up with a structure that looks like this with 2 bonds, what we call a double bond in between them. And it's actually true that almost all the oxygen in the atmosphere and stuff is not a single element, but instead one of these what they call diatomic molecules. So all the oxygen that we breathe and stuff actually exists as O2. It's also important to note that a double bond is going to be shorter than a single bond. It's similarly true for nitrogen, only in this case we can actually pair off 3 to form what we call a triple bond. And again, this triple bond is going to be shorter and stronger than a double bond, and quite a bit shorter and stronger than a single bond. When we start to have more complicated covalent molecules, we have a list of like a procedure to follow that's going to help us to draw their Lewis structures. The first thing on our list is going to be to determine the total number of valence electrons. That's for the whole molecule. We're going to remember that for cations we're going to subtract an electron, and that for anions we need to add electrons. Next, we're going to draw a skeleton structure. We're going to arrange the atoms around a central atom. This central atom needs to be the least electronegative atom. And then we're going to connect each atom to the central atom with a single bond. So we will have used up some of our valence electrons forming those bonds, but the remaining ones we're going to distribute to fill the valence shells around each atom. And then if we still have full valence shells and there's still electrons left over, we're going to place all the remaining electrons on the central atom. And then finally, we'll rearrange the electrons to make multiple bonds where necessary. Let's take a look at an example of drawing a little bit more complicated structure. and we will draw a Lewis dot structure for silicone dichloride. There's actually supposed to be 2 here. Let's just add that guy in. Oh, there we go. First, we'll take a look at the electronegativity of each of these guys. And we're going to see that silicone is going to be the least electronegative. It's going to be in the center of our Lewis dot structure. Next, we'll calculate all of the valence electrons for this molecule. Silicone has 4. There's 1 silicone, so we've got 4 valence electrons from him. Chlorine has 7 valence electrons. There's 2 of those, so we got 14 valence electrons from chlorine. And then we have the 2 hydrogens. Each one of those has a valence electron. We got 2 electrons there. 4 plus 18, or 14 is 18, plus 2 is 20 overall electrons. We'll place the least electronegative silicone in the center, and we'll draw out some bonds to each one of the adjacent chlorines. And at this point, we don't really have any reason to put the hydrogen across from the other hydrogen or the chlorine across from the other chlorine. It wouldn't have really mattered how you put this together. We'll remember that hydrogen already has its valence shell filled, right? Because it only had 1 to begin with, so we can't put any more electrons around that guy. And we're going to remember that each bond holds 2 electrons. So we made 4 bonds. That means we've already used up 8 of our 20 electrons, and there are going to be 12 electrons that still need to be placed. We'll start filling out around the chlorines here. So we'll have 6 here that fill out the rest of the valence shell for chlorine, and we'll put 6 here that are going to fill out the remaining valence shell for that chlorine. Now each Cl takes 6 electrons to fill their valence shells, and all of our electrons have now been used, and we've drawn out a reasonable Lewis dot structure for silicone dichloride dihydrogen. Let's take a look at another example here, and we'll draw a Lewis dot structure for CO2. And when we look at their electronegativity, we see that carbon is the least electronegative, so we're going to place it at the center. When we calculate our valence electrons, we know that carbon has 4 and oxygen has 6. There's 2 oxygens, so we got 12 electrons from oxygen, 4 from carbon. We add those together, we see we get a total of 16 valence electrons. We'll place carbon at the center and draw out our skeleton structure where we draw a single bond to each of the oxygens. And then we will go through and start filling in the rest of the valence on the oxygens. We'll see that oxygen has 6 or 8 electrons, 6 lone pair, and 2 bonding electrons. Carbon has 4 bonding electrons, right? So carbon here is not filled with all of its valence now, right? It only has 4 electrons. It wants 8. Oxygen does have 8. So if we imagine now that this lone pair goes to be a bonding, to form a bond here, and this lone pair goes to form a bond here, then we wind up with this structure. In this structure, oxygen has 8 electrons. It's got the 4 lone pair electrons, 1, 2, 3, 4, and 4 bonding electrons, 2 in each one of these dashes. Carbon also now has 8 bonding electrons, right? Because it's got 4 dashes going into it. Each of those has 2 electrons. So now everybody's happy. Up here, carbon was not filling its inner octet. It only had 1, 2, 3, 4 electrons associated with it. And down here, both the carbon and the oxygen now have their full octets. Okay. In this example, we're going to start to take a look at a little bit more complicated structure, the nitrite ion, where we're actually going to have a negative charge. So let's start off by taking a look at the number of valence electrons we have. We get 5 from nitrogen, we get 2 from oxygen, and we get 1 from the fact that it is a negatively charged species. So we get this extra electron that we have to remember to add in there for a total of 18 electrons. I didn't explicitly draw it out this time, but nitrogen is the less electronegative one. We're going to place him in the center, and we're going to draw out our skeletal structure. We now have 4 bonding electrons, and we have 14 remaining that we need to place. Once we fill out the oxygens, we're going to see we have 1, 2, 3, 4, 5, 6, 7, 8 here, right? Similarly, we have 8 here. There's still 2 left to place, and those 2 go on the center atom. And that is what they were saying when we had step 4 in our procedure. If we take a look here, nitrogen still has 6 electrons, right? It's got these 2, 3, 4, 5, 6. So it's going to want to form another double bond with an oxygen. And now we see that they both have the 8 electrons that they're looking for. And we can draw this inside of some square brackets to indicate that, so that we can put this -1 charge on here to indicate that this overall molecule has a -1 charge. Now, there is something called formal charge, and I'm not going to get into it too much with you guys, but what we'll actually find if we were to do the formal charge on all of these guys is that that -1 is actually associated with this oxygen right here. This guy has that extra electron. Now, placing that negative charge on there actually only really becomes important when we start to talk about things like resonance. Okay? And what resonance is it's pretty clear that we could have made that double bond between this nitrogen and this oxygen, or we could have made that double bond between this oxygen and this nitrogen. Both of these are completely equivalent to one another, but they are different, right? This is almost like the difference between your left and your right hand. They look the same, but they're mirror images of each other. And we can actually think about them moving between this form and this form, where this lone pair moves to here, and then this bond moves back onto that oxygen. And in fact, what winds up happening is exactly that. It doesn't stay simply with one nitrogen double bound to one of the oxygens and singly bound to the other oxygen. In fact, it switches back and forth very, very, very rapidly and winds up giving you properties that aren't the same as either one of these structures. Instead, the nitrite ion is going to be a hybrid of the two, which leads us to something called the resonance hybrid. Okay, and what we do is we'll draw that out. Here I've given this like a little bit of three-dimensional structure here, just to be a little bit more clear. This guy is not a, I forgot my double bonds. these lone pairs are still here. These guys are not linear because of this lone pair here. So that's why I'm drawing this like this. And then rather than draw out an explicit double bond to one of the oxygens and a single bond to the other one, I draw this dashed line right here. And that indicates that that bond is, the double bond here is actually shifting between the two. And what winds up happening is we know that this is true because we can measure bond distances now. And if we measure this bond distance, we don't get a single bond distance. We don't get a double bond distance. We instead wind up getting a 1.5, 1.5 bond distance between each of the oxygens and the nitrogens. They are the same distance for both of these. So there is no existence of a true double bond or single bond in this resonance structure. Here I have drawn out explicitly a molecule known as benzene. This structure with the 6-membered ring made out of carbon with these double bonds that alternate between them. This is very important in organic and biological chemistry. It's a kind of structure that pops up over and over again with different kind of variations on it. Benzene itself, being the simplest form of this, is like a big component of like gasoline and stuff. A lot of the smell you smell at a gas station on a hot summer day is actually benzene. And it's actually toxic and carcinogenic, so try not to smell that too much. But what could happen is it's pretty arbitrary whether I draw the double bonds here or I draw the double bonds in the other alternate positions. And in fact, they could be either one, right? So over here where I had to have a negative charge that was moving across from one end of the molecule to the other, here, by creating a ring structure, I still can do that without having any sort of charges. And we can draw the resonance hybrid for benzene like this using our very condensed notation, where we just assume that every single corner where two bonds meet holds a carbon, and that that carbon is going to have hydrogens attached to it, however many it needs to fill out its valence. And then we indicate that there is a resonance going on where these bonds are constantly alternating between them by drawing a dashed circle in the middle. And again, if I measure any one of these bonds, I'm going to get a bond length that corresponds to 1.5 bonds. Now let's take a look at how we draw Lewis structures for ionic bonds. So here I have sodium chloride, and we know that this electron is really going to be given to chlorine in this case, due to the difference in electronegativity. And I'm going to draw those by putting sodium here. I'm going to put its charge there. So this is the Lewis structure for an ion, right? And then in brackets here, square brackets, I'm going to draw the Lewis structure out for the chlorine. And I'm going to put its charge on the outside. I'm going to associate them next to each other to indicate that I have now an ionic bond. Here I have calcium, and we'll imagine it associating with two fluorines. So one electron is going to go to one fluorine, the other electron is going to go to the other fluorine. And then I can draw this out by drawing out my Lewis structure for calcium, and then placing the two fluorines next to it with their associated charges. And I can do it the other way. Here I have potassium with an oxygen, and I can draw out potassium oxide by having my 2 potassiums here, and then the single oxygen here with its charge. And we'll always remember that if we added up all these charges, +1, +1, -2, we should be getting 0 for the overall structure.